Are you trying to decide between Cloud SQL, AlloyDB, and Spanner to run Postgres on Google Cloud, but finding it's difficult to choose the best option for your unique case? How best to run Postgres on Google Cloud is actually a somewhat complicated question. The simplest way might be with Cloud SQL, which not only supports Postgres, but other RDBMSs as well. It offers a pretty simple experience in how we provision and manage those instances. However, we've seen newer offerings in the Postgres space, like AlloyDB, which has come out as a very powerful and performant, as well as Postgres-compatible database. Finally, we have databases that are quite different from Postgres, but have Postgres interfaces for their use, like Cloud Spanner. Now, all three of these databases are Postgres compatible, but they all have very different benefits, trade-offs, and cost profiles. In this video, we're going to look at setting up all three of these databases, and we'll also, as we go along, tabulate the important information. So let's jump into the Google Cloud Console now, and we'll start off with the Cloud SQL option. We're going to create an instance and specifically choose Postgres. As the screen implies, we have a great degree of flexibility on the database engine. Here, we can not only choose Postgres, but also MySQL or SQL Server, and we have a really wide range of Postgres versions available. While we're on this page, let's go ahead and capture some of this information. We'll give our instance a name and capture the password. Next up, when we get into the configuration options, we have a sort of easy button for selecting popular configurations on availability, performance, and cost. However, these options are actually configurable at a more granular level, so we'll skip this top option here and explicitly set all these parameters. In this region, we can see that we have really wide availability as far as the regions and zones go. We can even specify specific zones for our primary and secondary. This is an important detail to capture as well. So we have a few options here. Again, it's being somewhat opinionated, showing us ways that we can pick common configurations for our instance. However, we can always do a custom configuration. We can have up to 96 CPUs, and there's an associated memory range for each level of virtual cores. We can even get into the territory of shared core instance types if we really wanted an exceptionally low-cost instance. For our demonstration, we'll select a lightweight instance with a single virtual CPU core and about 4 GB of RAM, but also make note of the machine configurability here. It's important to note that while we have a pretty good selection over the CPUs and memory, we don't have things like CPU architecture selection. Google is being prescriptive in some of those details. What's nice with the storage here is that we have multiple classes of storage that we can select, and then we can also have automatic storage increases. So we can start pretty low for our database, and then the storage will be incrementally and permanently increased as we near our capacity limit. The networking here is pretty straightforward. We can either have a public IP for access, which requires the use of authorized networks, or we can use an internal Google-hosted VPC IP address. This latter option requires us to have a private Google connection that links our VPC up to Google's. Point-in-time recovery and backups are pretty highly configurable. So let's note that as well. For our test, we'll go ahead and leave the automatic backups off and keep deletion protection here. The other features here are somewhat less relevant, although the query insights is quite nice. This feature allows us to detect and diagnose performance issues, and we can enable additional optional features on top of that. This is worth capturing in our table. Let's go ahead and create this instance. Then we'll talk through how we can use this instance, think about and configure it, and add some additional metrics to our comparison before moving on to our other RDBMSs. Once our instance is up, we can do a quick walkthrough. Even though we have a public IP here, we do need to have some additional networking configured for our connections to this instance. We have some nice health checks and a lot of really nice views and titles here to be able to understand our SQL instance. Because we turned on Query Insights, we'll have some insights on our SQL. The System Insights is based on things like CPU utilization, disk utilization, and errors. Being a fresh instance that we're not actually using for anything right now, there's not a lot to infer there, and that's going to be the same case for the Query Insights. But based on these two dashboards, we can nicely right-size our instance and manage our SQL queries in a data-driven way. Let's go ahead and add the System Insights to our notes. Here's where we have the Connectivity and Networking Overview. We can revise our networking, run a connectivity test, and then manage the standard things that you would expect in Cloud SQL, like our users, databases, and backups and restores, all of which can be done through the console. We'll talk about replicas in just a moment. We might call these database objects, and we'll say that we have console options for visibility and management. Now, with any Postgres database, you're often going to want read replicas, and doing so is pretty seamless here with Cloud SQL. We can size our read replica independently of the primary read-write instance and have lots of different settings here specified specifically for the read replica. Just to see what this looks like in the console, I'll go ahead and leave all these settings the same, which are largely inherited from the primary instance. Then we'll take a look at what this read replica looks like in the console. With our read replica now created, let's go ahead and click into that. Here, we can see the read replicas showing up with the same sort of tabs for our replica instance. If we go to the SQL Instances page, we see the read replica nicely nested under our primary read-write instance. To summarize, Cloud SQL is a pretty standard way to have managed Postgres and offers some nice interfaces and controls for us to manage this in a serverless way. If I go to the Compute Engine page, note that nothing shows up here because this instance is running in Google Managed Projects and VPCs. So we need to make sure that we connect our networking to these instances if we're going to use private access, and you'll see that as a common thread across all these instances. We're going to get a nice managed experience. Let's go ahead and shift along to AlloyDB now and look at some of the configuration options available to us. We'll need to enable a separate API. Now we'll go ahead and create a cluster. Right off the bat, we're going to need to select a configuration for this instance. We need to select basic versus high availability, with high availability meaning a regional setup with zonal failover. In addition to that, we do get the ability to have read pools. For an apples-to-apples comparison, let's do a highly available instance with read pools and continue along. This piece is important. We see that we have Postgres 14 compatibility. This is not an option that we can adjust, and so we need to keep in mind here that we're much more controlled on the Postgres version. Let's note that in our comparison. For our networking, we'll need to provide a network that has private services access. Since we don't yet have that for our VPC, we'll go ahead and configure that now. Just like before, we have a safety net with backup options such as point-in-time recovery offered by Google Managed Continuous Data Protection. It's essential to highlight that there's a slight change in the networking landscape between Cloud SQL and AlloyDB. On the Cloud SQL side, we can leverage and control public networking, while AlloyDB allows only private networking. Moving forward, we have the standard encryption options around customer-managed encryption keys, but we'll leave that unchanged. We'll first set up our primary instance and then configure our read pool instances. Although there's some flexibility, it's somewhat restricted for sizing as we have only fixed increments of 2 CPUs and 16 GB of RAM going up to around half a terabyte of RAM and 64 virtual cores. Let's jot down the machine configurability details while they're fresh in our minds and add our read pool. Similar to the Cloud SQL situation, the read replicas have their configurability around sizing and basic parameters. We'll stick with a single node, keeping it small yet efficient for creating our cluster. Now that our instance and read replica are set up, let's survey the console. We're in our primary cluster and we have access to query insights, covering both primary read-write instance and read replica, as well as monitoring with significant overlap to the system insights in the Cloud SQL instance. There's also a dedicated page for data protection that provides us with a user-friendly interface for backups and restores. Heading to our AlloyDB main page, we spot our primary instance and read replica nestled together in our primary cluster. We can point out a few things here. Firstly, we have some system and query insights. We can also note that the storage type is fully managed, meaning we don't have to handle initial storage allocation and set auto-scaling. It's a smooth sailing experience, and we won't be charged extra for storage costs on read replicas. The only downside is that there's no good interface for exploring database objects like users or tables. Additionally, we want to throw in another performance metric since we can expect varying performance profiles across Cloud SQL and AlloyDB. Google's notes on this service imply that we get 4 times faster performance for transactional workloads and up to 100 times faster analytical queries than standard Postgres. In many ways, it's like a super smart, tailor-made, and cutting-edge database from Google with the Postgres outfit, making it Postgres-compatible while not being a standard Postgres database underneath. Let's document the performance differences between these two options. Lastly, our wildcard option, Spanner, is a unique entity compared to the others. Let's dive into the interface and explore it further. Cloud Spanner stands out from Cloud SQL and AlloyDB options due to its multi-regional option. Picture it as having your Spanner instance stretch across Iowa, Oklahoma, Belgium, Taiwan, and South Carolina, covering an enormous part of the world. Read replicas in more remote areas likely exist for latency reasons, while actual read-write replicas cluster regionally. Nonetheless, it's an impressive global scale that we have with this service. Let's choose a more budget-friendly option and go with the multi-regional setup just within the US. Instead of detailing machine configurations with CPU and RAM, we'll focus on sizing our units in terms of nodes or processing units. In both cases, these serve as units of consumption and scale, with the minimum being about 100, significantly impacting maximum storage capacity and compute costs. On top of the multi-regional configuration, we have additional flexibility to add more read-only replicas if desired. With everything set, let's create our instance. The initial configuration of our Spanner instance is relatively minimal, but as we'll see shortly, we still possess some configuration choices that we found in other RDBMSs. They're just created and configured after the instance has been launched. Let's record our observations so far. Determining the answer for Postgres versions is a little bit tricky. We're a little bit restricted in some of the Postgres support, and we don't explicitly get a version compatibility for Spanner. In the documentation here, it talks about the Postgres interface, and we can even go into the language support, but we don't get an official Postgres version. Also, this has scaled back compatibility. Our database engine flexibility is fairly low on this one as well. We have the option for Google SQL in addition to Postgres, but overall the options are limited. Now we actually have a global option for high availability here with regional level replicas. Our machine configurability here is relatively low. The storage is managed with a pay-per-usage model, but there's a maximum that's tied to the processing units. So let's explore some of the other options now in Postgres. We do have some interfaces for managing things like databases, some import-export options, and then a separate interface for backups and restores. Somewhat strangely, we actually don't have the option for automated backups directly. However, we do have good support for that through APIs and CLIs, so you can create a script that automatically does backups, but that's not going to be managed for you. We do get a pretty nice system and Query Insights interface to be able to understand and manage our instance, in addition to log insights and transaction insights. There are a lot of different pages to be able to explore our instance and manage it for performance and cost optimization. Now, in terms of the networking here, we're going to be using SDKs and integrations that rely on more domain level, multi tenant type endpoints. We do have security mechanisms and can do this in private and public ways, but note that the networking is somewhat prescriptive and we don't get our own IP here. One thing that we do really like about Spanner is that if we go to the overview and create a database, we'll get access to a new level of interfaces for working with our cloud database. This is not an option in the earlier options we reviewed. For example, we can run queries, including DDL, right in the console. We'll get results and explanations back. We can even set up change streams to stream our changes to analytic systems and get an additional piece of observability with this key visualizer, which will help us optimize our tables and databases. We'll go ahead and create another metric for interactivity, which is going to be low on the Cloud SQL and AlloyDB sides and great for Spanner. Our performance for Spanner, especially because of its global scale, is going to be great. This is a powerful service, and in our experience, you're going to get some really impressive performance. To finish out our table, let's create one last metric for something everybody cares about, which is cost. Now, this is going to be somewhat hard to compare across Spanner and the more traditional Postgres databases, given the different pricing units, but we'll try to share what we can. We can calculate example costs, and you can calculate costs for your own specific scenario using the Google Cloud Pricing Calculator. If we compare Cloud SQL to AlloyDB, we'll input some basic values for a relatively small instance and compare. Now, we're not able to compare exactly apples to apples because of the difference in machine size configurability here. But just to give an idea, we'll put it in an example. Now, if we look across our two examples here, note that we're paying a little bit more for AlloyDB, even though we have less CPU and about the same amount of RAM. The increased pricing for AlloyDB is pretty typical. You'll need to price out your own situation, and especially if you have an unusual case or very large or small instances, these dynamics may be different. But we find that AlloyDB tends to be a little bit more expensive than Postgres. That said, it may be worth the premium considering that we can see significantly faster performance on the AlloyDB side. Now, while we can't price it out exactly, we'll put in a Cloud Spanner instance and leave it at regional to try to be as similar as possible. The minimum size is 100 processing units, but we probably want to bring that up a bit. We tend to see that when comparing across the three, Spanner ends up being a little bit more expensive, but note that we're getting that global scale and quite the extensive technologically advanced implementation. So while your use case may be different, Cloud SQL is typically the cheapest, AlloyDB is in the middle, and Cloud Spanner is the most expensive. And now that our table's filled out, let's mark the winners. We definitely have the most flexibility for our database engine on Cloud SQL, but Spanner completely dominates the other options in terms of global scale and ability to span geographic regions. We get the best machine configurability with Cloud SQL, but that does also come with additional responsibility to tune CPU and memory. As far as the storage provisioning and model, we think AlloyDB really wins out here since it's a fully managed approach that is disconnected from the processing and compute. So we get the advantages of not having to manage the storage, and we get the auto scaling, but we don't have to tie the maximum storage capacity to the amount of processing like we do with Cloud Spanner. Cloud SQL and AlloyDB both have strong capabilities in terms of recovery and backups, with the offering from Spanner being a little weaker. But in terms of insights, we have really rich interfaces for being able to understand and manage our Spanner instance. We get some pretty nice control and visibility over database objects with Cloud SQL, and also have the easiest setup as far as networking is concerned. If you're looking for performance, AlloyDB or Spanner are certainly going to be the best options for you. Spanner has the nice benefit of having some rich interactivity and interfaces for working with your data directly in the console. Finally, in terms of cost, Cloud SQL tends to be the winner and will keep your cloud bills lower than the other options when we look at apples to apples for sizing. But keep in mind that a price performance analysis could change those pricing dynamics. Hopefully, we've helped you understand the high level for comparing these Postgres databases, and hope that one of these options jumps out at you based on what's important and what's not important for your specific use case. We'll keep an eye on the comment section for any questions and want to thank you for watching. Please enjoy responsibly.